Okay, good afternoon. And we are into last chapter, chapter 10. Okay, as I said earlier, chapter 11, you have to study yourself, and this is about the abacus and all. The abacus tutorial is there. So, this is not something we can teach on board. You have to go try yourself. And if you need any help, okay, so you can let me know. And also, we have our TA, Mr. Sanjay Singh. He can also, you can send him also email. If you have anything like you are working there and you are stuck with some problems, also with software, you can also contact him. So Sanjay, help them if they want. Okay, so uh, it's very important that you learn also calculus, as I told. The that's open source management software, and it is you can actually do it very well. The format also is for similar to the abacus. We discussed this earlier. Now, coming back to chapter number 10, since we so far we have the what we call the strong form, yeah. And this we had before, and then what? By x4, and then equal to our x
ERD for you by right.
Okay. So this goes here. Okay. So now this, of course, this will have some boundary condition, and you can see the example. The example will be, for example, you take two examples. Maybe one example is here. Here you are fixing like this. This is the problem you are going to solve. This is L, let's say, and EI is given for it. This is x equal to 0, x equal to L, and which all things are given in this case. Boundary condition, if you want to constitute for this one, then which all things you will know. Right. What you know is uy at x equal to 0 is equal to, so you are assuming uy from here. So uy x equal to 0 equal to 0. Then uy x equal to L is equal to. So let us say it's volume delta. So we line it equal to delta. Then angle, right? Angle is theta is equal to d uy dx at x equal to 0 is equal to 0. Slope is 0, and here also slope is 0. So we write theta x equal to 0 is equal to, and theta x equal to L is equal to d uy over dx x equal to L. So all based on displacements only. Here there is no boundary condition involving the moments and forces. Yeah? But actually they are boundary conditions only. Yeah, so you can actually solve it. Here for this one, Px will be equal to, this will be 0. Huh? there is no force distribution. Yeah. What external means? When you had a distributed load, then only there will be Px value for it. Since there is no distributed load over the beam, hence there is no. Okay, so and you can solve it, right? So it's very easy to solve. And how will you solve it? Now we are learning how to solve this, right? So analytically, you should be able to do it, right? Always we try to do solve analytically first, just to see how to do. And when you try to solve it, you will your equation is basically the Px equal to 0, and that makes it Pi d4 Ui over dx4 equal to 0, or simply d4 Ui over dx4 is equal to 0. Right? And hence your solutions will be simply Ui is equal to we can have A, and write A, let's say alpha, and then plus beta, then the value will be of x, so beta x plus gamma x square plus delta x cube. Will there be any other power of x? Right. Okay, and you have 4 boundary conditions you can apply over it, you can find out the value. So Ui at x equal to 0, you apply there, and that becomes alpha. That is equal to 0. So you get alpha equal to 0. Okay. Now from the third one. So this is 1, 2, 3, 4. This is a repeat of solid mechanics actually. Yeah. So number 3, if you apply, then we have duy over dx is equal to, you get beta plus 2 gamma x plus 3 delta x square, right? So duy over dx at x equal to 0 is equal to beta is equal to 0. So we get alpha and beta both equal to 0. So finally, y is of the form of gamma x square plus delta x cube, and then uy at x equal to L is equal to delta, and we write alpha L square plus delta L cube, right? And hence from here you can find out that gamma plus delta L is equal to delta over L square. Gamma plus delta L, right? So this, let's say, is equation number 5, and similarly duy over dx will be equal to, based on this, will be 2 gamma x plus 3 delta x square, and duy over dx at x equal to L is equal to 2 gamma L plus 3 delta L square is equal to 0, or 2 gamma plus 3 delta L is equal to 0. So you have this equation and you have this equation. This is 1, and then gamma plus delta L is equal to delta over L square, and we are going to solve it, right? So you do multiply by 2 here and minus it, right? Then whatever. So what you get is 0 plus delta L is equal to minus 2 delta L square, right? And you get this delta is equal to minus 2 big delta over L cube, right? And hence from here you can find out the gamma, and the gamma is equal to minus, so delta L, right? So minus, then you get 3, then delta minus 2 big delta L cube times L divided by 2, right? Or gamma is equal to minus plus, so you get 2 delta, not 2 delta, 3 delta, 3 delta L square. Okay, so we got the form dy is equal to okay, so 3 delta over L square x square plus minus 2 delta over L cube x cube. So this is how you solve it, yeah. And rest you can find out other reactions. Yeah? Okay. So once we know that, if this problem, as you know, that if you have this kind of problem, you will also have some moments, n moments and forces, and how do you find out which direction it has? You can find out from here, from equation, but just see, if you have some beam which is something like this, okay, then if you don't apply any force, you just have the two ends, you are just moving one up. Because of the hinge, this will be a straight line. But you are enforcing that slope is 0, so you have to apply a moment like this. Okay? This way, you have to apply a moment. Similarly here, you have to apply a moment this way, so that slope becomes 0, slope becomes 0. So you know the moment will be like that. Yeah. Now, just if you apply a moment like this, and what happens? If you try to rotate, go up. Then, if it is going up, then you want to bring it back, right? So you have to apply a force downward. So the mechanism can feel, you can sense that it has to be like this. Similarly, if you apply like this one, because clockwise, this will try to rotate like this. Yeah, so you have to force it up to retain it. And this has to be the same force, as you know. This moment and this moment will be same because of symmetry, not because they are balancing. They are in the same direction. They are not balancing actually, but because of symmetry, should have the same moment. So what is the value of M and what is the value of V is the shear force. So we have to find out that. So how to do it? Then we have to get the definition of those values. Yeah. And what is the definition? They are related. And how they are related? Tell me how they are related. Say again.
M is equal to VI divided by H square.
So this is the equation, right? And hence we are going to double integrate. So M from here d square y e x will be equal to, can get from 6 delta x over a square x minus huh?
We did it next verse.
minus 6 delta over L cube x square. Okay, now next d square uy over dx square is equal to, how do you get here? You get 6 delta over L square, right? And then you have minus 12 delta over L square.
Q. L Q.
You?
L Q. Q. 12 delta over L Q.
Oh yeah. Okay, so now we can have this d square uy dx square at x equal to 0 is equal to 6 delta over
L Q.
L.
Q. And begin L minus 2x.
This will be L square.
L square. L square.
Okay, and hence EI m at x equal to 0 is equal to EI L square uy over x square x equal to 0 will be equal to 6 EI delta over x square. Okay, so what we get here is m equal to 6 EI delta over L square. And this will be like this because when we derived it like the sagging is positive. So both the sides, from this side clockwise is positive, from this side anti-clockwise is positive. Okay. Well, if you put x equal to L, you will get, put it here, L, you get minus. Minus means it is clockwise here. The other end it's hogging. Yes, you will get minus. So m as such we are writing m as, you can write as m1 is like this one, and m2 just write m2. Probably we write like, let's call it m only, and we call it m1, we call it m2. Yeah, and we say that m1 is equal to minus m2 is equal to.
If we substitute x is equal to L by 2,
Huh?
it's coming out here, so if we substitute x is L by 2.
Yeah, so that is at L over 2, no? Yeah, moment will change, no? If you draw the moment diagram, then how will it look like? It will look like 0 तो होगा ही ना यहाँ, 2 0 here, no? Yeah, so this is m here, m here. Okay, now V, either you can apply the equilibrium condition, moment about this one. So we will what? This m plus this m minus V multiplied by L. Right? Will is the total moment, and from that you can find out, or you can use the equations. And what is the equation? M equal to V equal to what? V is equal to minus Vm over dx. Yeah. Okay, and hence Vx is equal to minus d over dx, and you have m. V has already derived it, right? And m is equal to ei multiplied by this, right? So we get is equal to ei multiplied by 6 delta over L square minus 12 delta over L cube. Okay, and hence we are going to find out is equal to minus ei, which is outside, we have minus here, and then we get 0 and minus 12 delta over L cube. And what do we get here? We get minus plus, so 12 ei delta over L. And it's constant, everywhere it has the same value. That really means it's positive at the right end, then it is upward, that how we assumed, and it is downward there. So we solve this one, and what we got? We can complete, we can draw, and what we get is the moment m, and we have this upward, no, this is downward. So this is m is equal to 6 ei delta over L square, where V is equal to 12 ei delta over L cube. Similarly, you get here, this is the V only, same value, 12 ei delta over L cube, and m is equal to 6 ei delta over L square. Here, know that from here to here is delta, right?
Minus 6.
Yeah?
Minus 6.
Yeah, but I'm writing the absolute sense. Yeah, so absolute sense. Yeah, given the, that is given the direction, not algebraic sense, but true sense. Okay. So basically here what we draw probably is not correct. So we have to write like this one, our M2 is wrong. Something like that. So arrow will give that whatever positive will be doing. Let this be negative, that means it is not. So we have that. Very good. Now, second problem I'm going to write, but you have to solve, and I will tell you what the answer is. And this problem is like this. So you have one end like this one, and we are going to, so here is a hinge as well. So this is the axis, but the beam is like, got it? What we are going to do is we are giving from here to here this theta naught. It is fixed otherwise, so we have like this. Yeah. And what is the boundary condition in this case? From here to here it is L only. What is the boundary condition in this case? So uy at x equal to 0 is equal to 0. Then uy at x equal to L is equal to duy over dx at x equal to 0 is equal to because, and duy over dx at x equal to L is equal to 0. Yeah. So you can solve it yourself. Yeah. I can tell you the answer though. Okay, so that you can use it. Okay, this means you can verify, not use it but verify, and this will look like. So here, and we have, yeah. So of course you need to have a moment. Since it is like this, you need to have a moment to actually do it like this. Otherwise, you will not be able to do it. So moment is required. The moment you apply a moment. Okay, so this will go down. Hence, you have to move it up. Yeah. Then what happens here? Similarly, there also, if it is like this one, this will tend to, if you have just a hinge here, this will tend to be like this. So from that, you have, if you are making slope 0, so you have to apply it like this one. And then you apply a moment, it will go upward, so you have to. Okay. So in solid mechanics, you feel the force. You know, so it's important that you should have some what you call huh? Visualization. This is more than visualization. See 7D. Like you go to mall and you go and see some 7D or 12D movies, something like that. You have to feel. Yeah. It's called insight. Okay. So this is, you should have some insight into it. Yeah. Now we have M here. We will have some M here. So in absolute sense, the direction as given, direction and magnitude, both are correct, right? And what is V? You can verify. M will be equal to 4 EI theta naught is equal divided by L. Yeah. So Newton meter, right? So this will be Newton meter square divided by meter, because Newton meter. So this will be this value. Here M will be equal to, let's call it M1. This call it M2. So this is the magnitude I'm telling here. When M1 is magnitude, M2 is magnitude. So direction will be here, and the M2 will be 2 EI theta naught over here. Half of it will be there. Now you can see the balance. We should balance. So this plus this will add, because both same direction, and this is going to balance it. So you can just add them. So 4 and 2, and then multiply. Then whatever you get multiplied by L should be this one, should be over L square in that case, because you're multiplying with L to balance it. Yeah, so V will be this plus this divided by L. So you get 6 EI theta naught over L square. Yeah. So you can verify this V will be the same value. Yeah. So this V is equal to 6 EI theta naught over L square. Okay. So you try yourself. Yeah. Any idea why we solve these two problems? If there is no idea, you can tell me. Okay, there is no idea.
We mix these two solutions that we can solve any kind of
Say again.
Maybe every solution will be a combination of these two.
Not really. Uh, well, maybe right in some way, but you don't have clarity. The clarity you will get once we do it. Yeah? Okay. Some step towards that, what you said. Yeah?
Structural application, you know, like, this one.
No, that's the motivation. That's not the thing. This finite element analysis, right? And let's go to basic definition of a stiffness. In the diet method, how we learn? In the lab, you have to find out what is the stiffness of a beam. How will you do it? Okay, you will do like this. You will have a beam. You will clamp it here. You will give a unit displacement here. Delta equal to 1. Right? Which will make it, if you give delta equal to 1, then how it look like? This will look like this. This will be 1. Delta equal to 1. But for a beam, K is when the all displacement you have to keep 0 except for the bounding, except for the degree of freedom we are talking about. Which all degree of freedom you have here? You have degree of freedom number 1, right? Then which one? Then you have 2, then you have 3, then you have 4. So you can have 1, 2, 3, 4. Right? You have 4 degree of freedom. So basically, if you have to find out K11, what you will do? Then it will be M. So let's call it M1. This is call it V1, M1, V2, M2. K1, K11 will be equal to M1, where Uy 1 is equal to 1, theta 1 is equal to 0, Uy2 is equal to 0, theta 2 . Right? This is how you remember, like we had a spring and then we stop here, we apply the U, X is equal to 1, and then we measure the force. Right? So our K11 was when degree of freedom 2 was constant, degree of freedom 1, you gave me displacement, you measured the force. And that was your, right? If this is K, F is equal to, you get K times 1 is equal to K. Similarly, come to the beam. What we are going to do? We apply a displacement in Uy direction, that is degree of freedom 1, keeping all 0. But if the moment to do it, theta 1 not equal to 0. We have to constrain it. And when you constrain it, it will look like this. Right? And this is equal to 1. And then what is the, in this case there will be moment, M. M1 is equal to, we have the value here. Right? Now you have to visualize, you have the other way around. Yeah, so if you take it up, moment will be in other direction, right? So value will be same though. M1 equal to 6 EI, delta equal to 1, so we write the over over L square. Right? All other are 0. So K11 is equal to what? 6EI over L square. Simple as that. This is anti-clockwise only. So K11 is 6EI over L square. Okay? This is your experimental method. It's not given in your book, but this is your insight basically. You should feel like you don't have to solve the equations basically. I mean, if you know these fixed end moment, you can find out like that. Then what do you have? Your V will be of what? Right? This is the V, V1. V1 is equal to, will be 12 EI. Delta is equal to 1 over LQ. Similarly, V2 here will be 12 EI over LQ. And then what do you have? Anti-clockwise, here also it will be. So M2 is equal to 6 EI over L. Now tell me what is K12? Given degree of freedom 2 is this. K12 is what? You are applying a displacement, unit displacement along first degree of freedom and measure the force along the second degree of freedom. Second degree of freedom is this. You find out what is the value of V. Whatever the value you get here, that will be the value. So K12 will be simply 12 EI over LQ. What is the value of K13? K13 is, okay.
So,
Yeah.
So V1
Got it. So first you have to, you are applying the displacement. Degree of freedom, we got confused, so this is not correct. So we have, so this becomes K11 because degree of freedom 1 is upward. So this is, and this is, because displacement is 1 and force is this much. Yeah. So this is K11. V1 will be K11. So this is K11 is this. K12 will be this one. So K12 is 6 EI. K13, 3 is this direction, which is minus, right? Minus 12 EI over LQ. And K14 is 41 is this. Yeah, anti-clockwise. So you have K14 is equal to it will not be minus, anti-clockwise, no? Yeah, so it will be 6 EI over A.
So if we look at the dimension of stiffness, in K12 we are getting Newton, and in K11 we are getting Newton. They are inconsistent by unit.
It is not consistent because your U is what? Your U is equal to U Y1 theta 1 U Y2 theta 2. So we should multiply to stiffness and give you the same dimension. So here the one which this multiplies to has to be in Newton per meter. The one to which this multiplies has to be in Newton. The one this multiplies to has to be in Newton per meter. The one to which this multiplies has to be in Newton. Right? Hence it's like that. So by design. Okay, so we got these values. Now you understand why we got this. Yeah, for a reason. Now we are going to do along the second degree of freedom. We are going to apply. Yeah? And we are going to do is along the second degree of freedom. We are going to apply this. That is theta naught is equal to 1. Okay, and hence we are going to find out M1 will be K22, right? So K22, so this will be K22. The force in this direction, the anticlockwise, this will be K equal to K21. We already have K12. You will wonder if it's the same value or not. It should match now, right? Otherwise, so here. Similarly, this K21, this is K31, and this is K. Now you match with this, with theta equal to 1, you get the value. What is the first one? KEI theta not equal to 1 over L, or EI over L. So K11, you get here let's start with K21. K21 is the one which is upward, 6 EI over L square. Well, does it match with this? K1 to K21 is matching, right? Now K22 is, this is our positive sense, as you know, like upward positive, anticlockwise is positive. So to that we have to match the actual direction. Here is, this is positive, this is anticlockwise positive, so we get exactly same value. So you get 4 EI over L. Similarly, K23, sorry, here we did some mistake. So this will be 24. So K23 in real sense, upward is positive, this is downward, so we get minus value. And K23 equal to minus 6 EI over L square. Yeah, then K24 is equal to, K24 is here, 2 EI over L. Okay. Guys, this is the way the UG finite element method is designed. This is the way I learned finite element analysis during my BTech, not those equations that came later on. Yeah, during my later studies. So Mixing it is important here. We have mixed audience. You know, we should also we have a student from computer science department, so we also have to actually show this, otherwise we don't know. Hence, I thought about actually solving this way. Now this we have that, and then now we have to compose k, give k. K11 we have so far 12 EI, so we can put EI in common. So EI over maximum we have L cube, right? So we EI over L cube. Yeah, and then we have K11. So EI over L cube, so we have 12. Okay. Next is 1, 2. 1, 2, 6 L. 6 L. 1, 3 is minus 12. And then we have 6. Okay. Fine. Then we have 2, 1, 6 L. And then 2, 2 is 4 L square. Okay. Minus 6 L. We can extend it further because it is going to be symmetric, because this is a elasticity problem. This will be symmetric. So minus 12 here, 6L here. Then you have minus 6L, 2L square. Okay, what about here? Yeah, one thing is 12 minus 12, these are forces, right? So they will match. So add them, it has to be equal to 0. So minus 12 has to be 12, right? 6L, we have to minus 6, right? So now similarly here, 6L, here 2L, this also, it will be here minus 6. What is this? This is, you see here, this and this equivalent. You have 6L, you have 6L, 2L square, minus 6L, minus 6L. What should be here? 4L square. This is like this. So you have like this, and right. So you need 4 EI over L. M equals to 2 actually. So you got the stiffness method. Yeah.
But usually you say that the column additions are 0, but
In this case it's not, because it's not simple in this case, because you have forces and moments both. If you had just forces, then you would get that. So hence this and this will match, but this will not match, because there is these are independent. They don't depend on these rows, but these rows depend on these rows. These two rows, hence balance will. So in a way, what we said was correct. Like both constitute the basic problems. Based on that, you can solve any problem. For a beam, now you can give any kind of displacement, you can solve it. Okay, so This is the stiffness matrix you have. Now, quickly in 5 minutes, if you can solve some problem based on, right? Now let us say you are solving a cantilever problem like this, and you have a force like this. Right? You want to solve this. What do you want to find out? Displacement. What is the displacement here? Let's say force is E. It is L here. EI is given. Find out Uy at x equal to L is equal to what? And duy, that is theta. Theta at x equal to L is equal to what? You can also find out what's the moments and all. Right? So how do you set up the problem? This is given here. Now you know that Ku equal to F. K is this, and U is equal to, what do you get? You don't know what the value is. You say Uy1, theta 1 is equal to 0, Uy1 equal to 0, theta 1 is equal to 0. Then you don't know what Uy2 is, that you have to find out, and what is theta 2, you don't know, you have to find out. So we have this. Right? Now F is equal to what? F, we don't know here what that is. Let's say we call it, first is V1, M1, right? Then you have here the of this minus P, and then no moments, you have 0. So you have this. Right? Okay, now you know that first two rows will not work. So finally we have, this is the one which is going to help. So we just write. So we have EI over LQ, and then you have 12 minus 6L, 12 minus 6L minus 6L, 4L square. Yeah, and then multiplied by, this is transpose by, okay, minus by U, Y2, theta 2 is equal to minus P, right? Okay, and then what do you get? Uy2 theta 2 is equal to L cube over EI, right? Then 1 over 48 L square minus 36. So 12, is it 12? L cube, L square, right? Determinant of that multiplied by, we get 4L square, 6L, 12 minus P is equal to, right? So simply get L cube, L over 12 EI, and then you have minus P, so you can have minus PL, because this multiplies to both of them, and then you have 4L square and 6L. So that's what you get. Yeah, so minus, accordingly you can simplify, you can get. But this is the value, you get the both of them. Both you get negative, that really means what? Displacement is downward and slope is also clockwise. So the slope is also clockwise. This is clockwise. So hence you get both of them. Yeah, and then you multiply K with The complete U, then you get all the forces and you will get the reactions. Right? So reactions, how do you find out the reactions? So Vm. So if you this multiplied by this, you get this, right? So basically, if you multiply this, so this one and two, third and fourth. So you get V1N1 is equal to, we get this one, minus 12, 6L, minus 6, minus 6L, and 2L squared. And of course, this is multiplied by the whole thing, so EL, EI over. No, K. EI. Yeah. Then you have multiplied by this. So basically, what will be this? And you have this one. U2, UI2, theta 2. You get these values from here, you get this one. This chapter is about this only, but not this method. Yeah. Now we have to use the equation shape functions to actually to get this K, but we solve the same way. Only thing now remains is how to define the shape functions for this problem and how to formally solve using mathematics. That's the thing. Yeah. This is as an engineer would solve. That would be more like a mathematician would solve. That's the. So that is all for today. Okay. Any question? Okay. If there is no questions, see you guys tomorrow. Also tomorrow we will have online class. Okay, not in the lecture. We will not come here. We will have online. Okay, and the same old link that we used to work with. Okay. Okay. Thank you. See you tomorrow.